In this video, we're going to go over how to write balanced redox equations using half reactions. So the first step to balance redox equations using half reactions is you're going to want to list out all the species mentioned in the question. So some notes about what you need to keep in mind when you are considering all of the species in the question is you're going to want to make sure that any ionic compounds, you're going to want to check if they are soluble in water. Okay, sometimes the question does tell you if they are soluble, but if it doesn't, then you're going to want to check out page 6 of the data booklet, the solubility table on that. Okay, now if your ionic compound is soluble in water, you're going to dissociate it into two ions. Okay, one would be the cation, which is your positive ion, and the other one is going to be your anion, which is the negative ion. So when you break up your ionic compounds, so when you dissociate them into their ions, you should only get two products. Now when we write ions, you're going to want to make sure that you include charges as well as states. And ions are always aqueous. For the next one, all molecular compounds stay together, so you're not going to ionize them. So these notes say dissociate, but the proper word is ionize. Okay, so what that means is you are not going to break up molecular compounds into their ions. How you identify a molecular compound is that they will have two or more nonmetals together. Okay, ionic compounds are when you have a metal and at least one other nonmetal. Okay, molecular compounds are also going to be neutral. So molecular compounds, you do not ionize them. However, they may be aqueous. But even though you may have a molecular compound be aqueous, it still sticks together. So for example, if you dissolve hydrogen peroxide in water, it goes from a liquid to aqueous. Next part here is all strong acids are going to split into two ions, and weak acids are not ionized. So one thing that you want to be aware of is that you have 6 strong acids, and you can find them on page 8 of your data booklet. Okay, so let's check out those strong acids. So going to page 8 of our data booklet, where I'm looking is above the gray hydronium line. So perchloric acid, hydroiodic acid, hydrobromic acid, hydrochloric acid, sulfuric acid, and nitric acid, those are your 6 strong acids. And while I'm here, I'll talk about the solubility table that I mentioned earlier. So that's on page 6, and that's this table right here. So how you use your solubility table to determine if a substance is soluble is first you locate the anion in the first row here, and then as you trace your finger down the columns, you find out where your cation is. Okay, so when you're in the second row here, anything that's found in the second row is going to be very soluble. Anything found in the last row is going to be insoluble in water. All right, for the next one, if you see the word acidic in the question, that means that you're going to list H+ ions as one of your species in your list. Now, if you see the word basic, you're going to list hydroxide ions. And then last but not least, all aqueous solutions contain water. Therefore, you also have to list water in your species list. So this one can be really easy to forget. So make sure anytime you see the word aqueous, you're listing water. All right. Step number 2, after you're done your species list, you're going to figure out, okay, what are all of your OAs and RAs, so that's your oxidizing agents and reducing agents, from your species list on the redox table. Then you're going to identify your strongest oxidizing agent and your strongest reducing agent, and how you're going to do that for your SOA is you're going to start in the top left-hand corner of your redox table on page 7 of your data booklet, and you're just gonna slowly scroll your finger down the list until you hit your first species on your list. Okay, you're gonna do the same thing for the SRA, but you're gonna start in the bottom right hand side, and you're going to slowly move your finger up the list of reducing agents until you hit the first species from your list. Okay, what's really important about this is you can only use OAs or SOAs or SRAs that are in your species list. If the reaction contains substances that you don't have on your species list, you can't use that reaction in the question. So that's going to be super important. Okay, so if you're looking for your strongest oxidizing agent, you're going to want to make sure that when you're looking at the reactions, so if we look here, okay, so let's say that we have a perchlorate ion, but let's say that our reaction isn't acidified. So we couldn't use this reaction as a half reaction to balance the question. Okay, so just watch out for that. Additionally, if we had for our RAs, if we had chloride ions but we didn't have hydroxide ions for our reducing agents, then this reaction right here we couldn't use. So that's what I'm meaning when I say make sure you have all of the OAs for a certain reaction or all of the RAs for a certain reaction in order to use it. So I gotta adjust this. Okay, that's a common mistake that students make, is they select reactions that they don't have all of the OAs for or all of the RAs for. So one last thing that we need to go over from step number 3 is that we're going to write the reduction half reaction from left to right. So what that means is when you find a reaction that you can use for the reduction reaction, you're going to write them from left to right as they appear in this table here. But for the oxidation reaction, you're going to write it from right to left. Okay? The reason being is because when we write these reactions from left to right, we're gaining electrons because they're on the reactant side. Okay? But when we write them from right to left, so what's on the right-hand side would then become your reactants, and what's on the left-hand side would then become your products, then in that case, the electrons would be lost if what's on the left-hand side of your reaction is on the product side. Okay, step 4, balance both half reactions so that the number of electrons lost is equal to the number of electrons gained. And then step 5, you're going to add the 2 half reactions together. All right, so let's do an example problem. Determine the net ionic equation for the reaction that occurs when a strip of aluminum is placed in an aqueous solution of zinc nitrate. So, step 1, we're going to list out our species. So I'm going to say this is species list. So it says that we have a strip of aluminum, so that tells me that that is aluminum solid. Now it's placed in an aqueous solution of zinc nitrate. So aqueous tells us that we have water. So I'm going to list water. And since it's zinc nitrate, typically if the question says it's an aqueous solution of zinc nitrate, that means that this substance can dissolve in water, but let's just get some practice in using our solubility table. So nitrate, we're going to find right here. Now I'm tracing my finger down and I hit, okay, most things with nitrate are soluble, but let's just keep on tracing our finger down and make sure zinc isn't in our list of exceptions. So I'm not seeing zinc nitrate anywhere here. So yeah, it does fit under most, so zinc nitrate is very soluble, so that means that we can dissociate zinc nitrate into its 2 ions, the cation and the anion. So zinc nitrate, the cation is zinc, and it's aqueous, it has a 2+ charge, and then we have nitrate, which has a 1- charge. Okay, so where I'm finding the charges is going to the periodic table. So if I find zinc, this is where it tells me that zinc, when it's an ion, it has a 2+ charge. And for nitrate, where I'm finding that is right here. Okay, so this tells me nitrate is NO3 with a 1- charge. All right, so now we've completed step 1. Now we need to do step 2. So we need to go through all of these species and figure out, okay, what is an OA, what is an RA, so on and so forth. Okay. one thing that I want to talk about before going through this entire list is that some chemical species are special, and they're special in the fact that they show up both as oxidizing agents as well as reducing agents. Okay, so I've highlighted the ones that show up as both oxidizing agents and reducing agents. Most of them have 2+ charges, or they're neutral. Okay, so the chemical species that show up both as an OA and an RA, we have tin, 2+. We have iron, so iron shows up here as an OA and here as an RA. Okay, so those are reactions that I just showed you. Sometimes it's easier to use the electric potentials on the right hand side. So if you're trying to find this on your own data booklet, the uppermost reaction is at 0.77 and the lower reaction is at -0.45. For tin, those reactions were at -0.14 and +0.15. Okay. Water also shows up both as an OA and RA, so you can find that at -0.83 as well as +1.23. Okay, and then last but not least, we have chromium. So chromium 2+ shows up as an OA at -0.91 and also at -0.41 right here. Okay, so those substances, they can be both oxidizing agents as well as reducing agents. Now that means that water here could be an OA or it could be an RA. Now, how I personally remember all of the species that show up as OAs as well as RAs, I remember it as, this is going to be disgusting, but it works. Creamy snot feels hot. Okay, so that's chromium 2+, tin 2+, iron 2+, and water. So we got the H and the O for water. Okay, so if you want to have a memory device that's a little less disgusting, go for it, but this is what works for me. All right, for the rest of these, let's figure out if they are OAs or RAs. So I'm going to be starting with aluminum solid. Because it's solid, that makes me think it might be an RA, but I gotta find it. So I'm finding aluminum right here. So at -1.66, that's the reaction that I'm finding this here. Okay, something that you might want to do to help you out. Some students use the sticky notes that have a little pointy end on them, and you can use those to point out OAs or RAs to yourself. Okay, because otherwise this table ends up getting marked up quite a bit. So I would recommend using sticky notes here. All right, so we have aluminum, that's an RA. And it's aluminum solid, not an aluminum ion. Okay, now we're going to find zinc 2+. So that I think might be an OA, but I'm not sure. So what I'm doing is I'm just scrolling down, skimming down just to see where I can find zinc. Okay. So I find zinc right here. So zinc 2+, that's at -0.76. So I'm just saying the numbers just to help you find it a little easier. Okay, so that's an OA. And for nitrate here, so I'm just gonna start at the very top, and again I'm just skimming through the left hand side right here to see if I can find it. Okay, so here's something important. We have nitrate here, but we do not have hydrogen ions in our species list. Now if I look at the question, okay, and just double check, okay, I'm seeing that it's not saying that this this solution here is acidified, so that's another kind of, okay, it's definitely not, we definitely don't have H plus in here. So because of that, because I don't have both nitrate ions as well as hydrogen ions, I can't use this reaction. Okay, so I got to keep on moving on. So let's look to see if we have nitrate lowered down. Okay. So we have NO2, but that's not the same thing as NO3 1 minus. Okay, looks like it's not on the left-hand side. Let's skim through the right-hand side. So I'm starting at the bottom, going up. Okay, so I'm not finding nitrate in my data table. Okay, that's okay. We're just gonna leave it. All right, before I move on to step 3, I'm going to go back to my redox table, and I'm just going to make sure I circle water on both sides. Where did that one go? Right there. Okay, just so that I have all of my OAs and RAs marked out. Okay, so step number 3, we need to figure out what is our strongest oxidizing agent, what is our strongest reducing agent. So for the strongest oxidizing agent, I'm going to my table and I'm starting in the top left hand side. Okay, I'm not looking at the right hand side of the reactions, only the left hand side. Why? Because that's where all of my OAs are. Okay, so what I'm doing is I'm taking my finger and I'm just tracing it down until I run into my first oxidizing agent. So I'm not going to stop at this reaction here at positive 1.23. Like, yes, I do have water in my species list. However, that's on the reducing agent side. I'm trying to figure out my strongest oxidizing agent. So I'm not stopping at this reaction. I got to keep on going because I'm finding my strongest oxidizing agent. Okay, so I keep on going. This is only highlighted because of the species that show up both as an OA and an RA, but it's not in our list. So keep on going. And it looks like the first OA that I run into is zinc 2+. So that has to be my strongest oxidizing agent. So let's go here. And that is my strongest oxidizing agent. Now we're going to do the same thing for the strongest reducing agent. The only difference is that I got to start in the bottom right hand corner. So I start with my finger down here and I move it up. Looks like the first reducing agent I bump into is aluminum. So that has to be my strongest reducing agent. Okay, so now that we've figured out our SOA and SRA, those are going to be the reactions that we use to balance the net ionic equation. Okay, so I'm just going to arbitrarily choose to use the strongest oxidizing agent reaction first. So that's zinc's reaction. So if I go back here, okay, I'm using this reaction right here, so I'll get rid of all this extra stuff. Okay, so I'm going to go zinc 2+ plus 2 electrons gives me zinc solid. Okay, so that's my strongest oxidizing agent, done. Okay, so remember SOAs, you write the reaction from left to right. For SRAs, you're going to write them backwards. So if I look at aluminum here, so I'm writing this reaction starting on the right hand side and moving over to the left hand side. So on my reactant side, I'm going to have aluminum solid, and then on my product side, I'm going to have aluminum 3 plus 3 electrons. And I like to line up the reaction arrows so that it makes it easier to see the product side versus the reactant side. So aluminum 3 plus aqueous plus 3 electrons. All right, so that is step number 3 done. Step number 4, we need to balance both half reactions so that the number of electrons lost is equal to the number of electrons gained. So what that's talking about is we need to figure out how to make these two numbers the same. So in other words, we need to figure out what is the lowest common multiple between 2 and 3. So that's going to be 6. Another way to say lowest common multiple is what is the lowest number that both 2 and 3 multiply to? Okay, that's 6. So what I'm going to have to do to the first reaction with zinc in it, in order to get the electrons to be 6, I need to multiply this entire reaction by 3. So that's going to mean I have 3 zincs. I'm going to have 6 electrons and then 3 zinc solids. So the most common mistake here is forgetting to multiply absolutely everything by 3, or by whatever number you're multiplying by. For the second reaction, in order to get 3 to 6, I need to multiply it by 2. So I'm going to make sure to multiply everything here by 2. So that's 2 aluminum solids, 2 aluminum ions, and 6 electrons. Okay. Now, since these electrons, we have the same amount on opposite sides of the reaction arrows, they cancel out. And they cancel out when you add up the reactions together. So now what I'm going to do, there's nothing else that cancels out, so now I'm just going to add up these reactions. Okay, so I'm going to start with the reactant side and make sure I write everything down. So I've got 3 zinc, and that should be zinc aqueous. Don't forget your states. And don't forget your charges either. Now, this 6 electrons canceled out, so I'm not writing it. But I'm going to move on to my next reaction. So I've got 2 aluminum solids. Gives me, and now I'm going to start with my products with the first reaction products. So 3 zinc solid plus 2 aluminum, 3 plus, aqueous. And then I'm not going to write the 6 electrons because they canceled out. Okay, and that's done. So one other thing that I'm going to add to this question here is just whether this reaction, so 3 zinc, 2 plus ions, reacting with 2 aluminum solids gives me 3 zinc solid plus 2 aluminum ions. So is that spontaneous or not? Let's figure that out. So remember that the spontaneity rule says that in order for a reaction to be spontaneous, the OA must be above the RA. So if I look, my OA is right here. My RA is right here. So if we read this from left to right, my OA is above my RA. And remember what we said in an earlier lesson, you could kind of imagine a ball on a hill. If the ball is rolling downhill, that's going to spontaneously happen. So this tells you it's a spontaneous reaction. Okay? So let's add this in. This wasn't asked by the question. I'm adding this in. This is a spontaneous reaction. I'm abbreviating reaction to RXN. Okay. Now, when question asks you for a net ionic equation, they're talking about this part right here. So this is a balanced net ionic equation, which I'm going to abbreviate equations to EQT. Okay, but this can also be considered a balanced redox reaction. Okay, why? Because we have both oxidation and reduction happening. This is my reduction reaction because the electrons are on the reactant side, so they're being gained. And this is my oxidation reaction because the electrons are on the product side, so they're being lost. One last thing about balancing redox equations using half reactions. If you have the electrons in both of your reactions, if they are on if they are both on the same side, then you're doing something wrong. You should always have one reaction with its electrons on the reactant side, so that would be your reduction reaction, okay, and that belongs to your SOA, and the other reaction should have the electrons on the product side, and that's going to belong to your SRA, okay.